Section. Let's put 20 minutes on that clock.
The van hotline, you need in the office. The van hotline, you need in the office.
Oh, that was our last test.
Yeah.
Our last.
Questions from 9-1. Last chance. I will answer my class.
What are we doing after that?
Figure out some controls.
Something else.
Questions from 9-1.
Yeah.
God bless you.
It did come out. You jinxed it.
Good. Dying slowly and painfully.
What?
You'd think his death was going to be this way, at least get it over with quickly.
Get to work.
Homework is due today. So. 25? I would happily do 25. I got a couple emails last night specifically asking about 23. I made sure to post a photo of 23 on the website.
We already have.
Yeah, I already did 25 in class.
She wasn't here.
Oh. Well, nobody else is speaking up, so you know what? I'm gonna do it.
Hey, we're gonna do it.
Alright, ready? So this is an example of one where there's no direct theorems or identities that get us to cotangent. But if I look at my cheat sheet, there's a couple that are going to be close, and by close I mean there's a reciprocal difference. In this case, the theorem I'm going to use, the identity I'm going to use, is the fact that tangent squared of x plus 1 is equal to secant squared. Now, I don't have secant squared to use identity, but don't forget, algebraically, I'm allowed to add, subtract, multiply, or divide both sides of the equation. I'm allowed to square both sides. I'm allowed to square root both sides. So what I'm going to do is I'm going to modify this Pythagorean identity by taking the square root of both sides. When I do, I end up with secant of x by itself equal to the square root of tangent squared of x plus 1. Now I can make a change. My secant equation is equal to the square root of tangent squared of x plus 1. Now this is not cotangent, but it's close. Cotangent, as a reminder, is in reciprocal identities as the inverse or reciprocal of tangent. So I can now modify this function, which is in terms of tangent, to make it in terms of cotangent. This becomes equal to the square root of, I look at my reciprocal identities, tangent is equivalent to 1 over cotangent. That also means that tangent squared is equal to 1 over cotangent squared. So end up with this equation, which is my solution. It is secant written in terms of cotangent. Thanks, man. Sorry, you look like you had questions.
That's it?
That's it. We changed the secant equation to look like it has to do with cotangent in it. That's it.
Oh. So it doesn't have to be just specifically cotangent, we just have to have cotangent.
Now, there were a lot of them in the homework that did end up just being like just the one you weren't looking for. But remember, it just says in terms of. That means it has to have only that trig function in it. It can have other, values like the square root, the plus, and minus, a number. There's no other trig functions. No sines or cosines. Just cotangent. That's some great math here. That was genuine to me. So now I just need a little.
Sometimes you just need music all the time.
I would play music during these kind of sessions, but then it gets banned for that.
It gets banned what?
I post all of these videos on YouTube once, and they ban it if it's got music, copyrighted.
You're videoing this, even though we're not doing it?
We're answering questions. Maybe some people who are not here have questions.
No, they won't ban it.
I also video it. Doesn't cost me much. Other questions?
Not yet. I can't even get on because of the Wi-Fi.
33?
Yeah.
Happily. Alright. 33 states the following. We have, ooh, yeah, verify the identity. Oh, man. So as a reminder, this is from last week, where we talked about how we have to algebraically manipulate one side of the equation only. Cosine squared of x minus tangent squared of x is equal to 2 minus sine squared of x minus secant squared of x. So, I have to first pick a side to start with. That is my main thing. And once I pick a side, I then look for algebraic opportunities, those listed. Pay attention to my solution to see if it can guide me, and if all else fails, convert things into sines and cosines. Let's start with picking a side. Left or right? Chloe, it's your problem. So, left or right?
Everyone will get you there.
They're actually both about the same for this one.
I guess so.
Okay. So that means I need to start with just cosine squared of x minus tangent squared of x. And I cannot stop manipulating this equation until I get to this. This is referred to as the left-hand side from last week. And I need to make changes to this function until eventually I get to the right-hand side. So I see a cosine squared minus a tangent squared. Now, there are multiple things you can do to these problems. I have the quotient identities, I have reciprocal identities, I have Pythagorean identities, I have even odd identities. I know that last one is not helpful because there's no negative signs in this one.
Can we turn that into sines and cosines?
We could. That'd be an option. I could try to turn it into sines and cosines. But for this one, it's actually a little faster. There's actually a little faster way. So now I'm going to look to my answer to see if there's a guide. So I look at my answer. I start with something in terms of cosine, but my answer has switched the cosine either into the sine or the secant. I have a tangent in my original problem. This has been converted into either a sine or a secant. So if I can find something that does one of those things, that's probably a good step to take.
You get to secant be a cosine.
I can, but I end up with 1 over secant, right? Which is not what I want. I want just secant by itself. So good catch. But again, I'm using my solution to see that's probably not a good step. So what do we think?
So there's a better option than putting it in there.
Yeah, there is. I'll give you hints. Look at your Pythagorean identities. So, what you have just discovered is there is a connection between tangent and secant. What was that connection? So we know that tangent squared of x plus 1 is equal to secant squared. Now, if you look at my problem, I don't have tangent squared plus 1. I have just tangent squared. So if I modify that formula a little bit, I could get just tangent squared by itself. So that's what I'm going to do. How would I have to work this equation to get tangent by itself?
You subtract.
Yeah, I subtract 1. I end up with tangent squared of x is equal to secant squared of x minus 1. So I'm going to use that. I'm going to come over here. This is now going to be equal to the cosine I have not modified yet, minus, but instead of tangent squared, I'm going to write what we just found. Secant squared of x minus 1. Notice I put it in parentheses because that negative is being applied to all of tangent. So this negative needs to be applied to everything I replaced tangent with. Now, I have successfully gotten this problem from cosine and tangent to cosine and secant, which is good because my answer has secant in it, but it doesn't have cosine. So how else can I modify this thing?
Cosine minus 1 or whatever.
Yep. So I have another Pythagorean identity. Sine squared of x plus cosine squared of x is equal to 1. This connects cosine and sine together, but again, I have cosine right now. I don't have cosine plus sine. So I want to, again, use algebra, get the missing piece by itself. So I'm going to subtract the sine over. I end up with cosine squared of x equals 1 minus sine squared. Why is that so good? Well, now I just replace anything that has cosine squared with this 1 minus sine squared. This is equal to 1 minus sine squared minus secant squared of x minus 1. This looks really promising. It has sine and secant in it, which my answer should, but these parentheses and some of the numbers are not quite lining up. So let me see if I can simplify this algebraically and get to what I actually want in the problem. Let's look at this problem now. No trig left, just algebra. This first of the parentheses, there's nothing on the outside of it. There's no constant, there's no negative, so I'm just going to drop them. This first parenthesis becomes 1 minus sine squared. The second set has a negative, so I must distribute that negative to both pieces. So this becomes negative secant squared, and the negative makes this a positive 1. If I look at my answer has a 2, but it does have a negative sign and a negative secant, so it looks like I'm really close. What do I have left to do? Yeah, just add the numbers. 1 and positive 1 together make 2 minus sine squared of x minus secant squared of x. This is my right-hand side, so I am finished. Notice how I use Pythagorean identities that specifically look like it's going to get me towards the solution. That is a great way to try it if you can do it. If not, like on the previous one, sometimes you have to find an intermediary step to get me closer. Those intermediary steps could be other trig identities. They could be algebraic in nature. Like when I showed you guys 23 in your Google Classroom, that one uses combining fractions, which is really common. And so, like in that kind of problem, along the way, it doesn't look like it's getting any closer to the answer, but it does by the time the end rolls around, because again, it uses algebra to get us there. Other questions? 8 minutes remaining. Thank you. I'm just doing substitution line.
Huh?
Just doing substitution line.
These things were
A lot of this section is just a lot of pattern recognition, a lot of substitution. That's what makes it fun. Yeah. Yeah. That's the word I use. Only if you see it. Not mine will be written in Hungarian. Any other questions?
It's a 39, right?
Yep, 39. The last one. I don't know the chords. Other questions? Show it to my next year.
Dude, that's bad. The Chicago Cubs have a World Series batting.
Huh.
That's bad.
Good. This is fine.
I didn't have a mask on.
What the heck, man?
I put it in my deck. So I really made you think, you know.
I do happen to have an extra. I haven't worn yet.
Huh?
I have an extra. I haven't worn it.
I'll just go to the locker room and get it. On my way to.
Okay. If there's no more questions, I'll also record the second block in case they have questions and stuff that you guys might want. I didn't receive any emails from the other people who were in the class either, so I guess we're good. All right. The next section, I want you to have 2 things out today. 2 things out. Your cheat sheet and your unit circle.
What?
Hope you got it.
No.
Or, like I said at the beginning of the semester, beginning of the year, hope you got it memorized.
I'll just take it out.
Yeah, you should probably take that. Alright? Bring out the unit circle, bring out that cheat sheet. The next section we're going to talk about deals specifically with a couple of alternative rules. I told you guys at the beginning of this section, and so the beginning of this year, that the unit circle contains the majority of angles talked about in trigonometry. But obviously, the unit circle is not every single angle, right? Look back over here on the side wall. A unit circle consists primarily of angles of 30, 45, and 60, and then variations on them, moving their way around the unit circle. But there's a lot of gap in there. There's a lot of pieces that are missing, a lot of angles that are not on that list. So, before the advent of things like calculators, how do they do it? Very simple. They had a bunch of formulas. Yay! Grab the unit circle up. Grab that cheat sheet out. Let's look at problems in this section. These are referred to as sum difference formulas, or I believe on your cheat sheet they refer to as addition and subtraction formulas. These allow us to take a single trigonometric function of a value we cannot calculate on the unit circle and convert it into one we can, using an addition and subtraction. Now this is also limiting, because only things we can add and subtract in the unit circle can we do this with. But it opens the field a little bit more. Each set of rules we're going to talk about, and we are going to talk about every single set of rules that is on that cheat sheet. Each set will expand what can be done by the calculator. As long as you know your unit circle and have that list of formulas, there is a lot of angles that for a long time, that's how they did everything. Every single part of mathematics was done this way. So, let's start by. Let's pose a problem. No calculators allowed. That cannot be solved without a calculator. Here we go. Sine
Come on, man.
of
2.
15 degrees. Now, 15 degrees is not on the unit circle. However, we can actually find the value of 15 degrees by modifying the function we're dealing with using one of these formulas. Now, to do so in this kind of section requires a couple of unique thoughts. I cannot think of this as a 15-degree problem. I have to somehow think of this as a sum problem or a difference problem. Meaning my 15 degrees is not 15 degrees. I can think of it as 5 plus 10. I can think of it as 1 plus 14. I can think of it as 20 minus 5. But the big detail is I have to think of them as ones that are on the unit circle. So 15 degrees is not 15 degrees. It is some combination of unit circle values. So, on my unit circle, my values. 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, 360, and the negatives of those. All of them are possible. There are many, many sets that either add to 15 or subtract to 15. We're going to use one and use it to find our answer without a calculator. Here we go. Sine of 15. How I do it is I can't think of this as sine of 15. I think of it as sine of 45 minus 30.
Oh, that's smart.
Why? 45 is in the unit circle. 30 is in the unit circle. Now, these are not the only ones I could have chosen. Alternatives. What if I chose 60 and 45? Those are also 15.
What about 225?
225 and 210? This process will work for those two. What if I chose positive 30 degrees, negative 45 degrees, and even odd rule?
No.
Oh, now I'm getting crazy. But this is how big the field starts to become. Because you can start to do things that before were impossible. And remember, the reason we talk about 30, 45, and 60 are because those come from very easy to find triangles that exist in the natural world. A 30, 60, 90 comes from an equilateral triangle. A 45, 45, 90 comes from cutting a square. So each of those can be easily found and identified in a natural system, but 15 degrees does not exist in one of those systems. I can modify to get there using these formulas. Now, how I have to do it, again, this is the first piece, the one that for some of you will be the mind-bogglingest of mind-boggling parts of the section. How the heck do I get those two numbers? I pick them. I pick them so that they do what I want them to do. I want 15. I find two that give me 15. We chose 45 and 30. Could have chosen 60 and 45. Could have chosen, what did you say, 225 and 210?
Oh, 350,
350.
No, 315.
315 and 300. Like any of these will work with this process. I just have to pick some. Now, more often than not, I'm old. I stick to the first quadrant when I can. It's the easiest to work with, especially if I'm doing it from memory. Because remember, after the first quadrant, you have all these weird sign changes and stuff going on, which makes it a little harder. So if I can keep it as simple as I can, it's better. All right, so now I've discovered that there is a set of angles, I'm going to use 45 and 30, that get me to 15 degrees. Cool. So how do I actually find the value without grabbing a calculator and plugging everything in? Well, I use one of these formulas. Now I have to match the formula to the problem I'm doing. So in this case, I'm doing a difference problem because it's 45 minus 30 to get me to 15. So I come over here to the sine function. There are two versions of the formula. One with addition, the sum formula. One with subtraction, the difference formula. I choose the second one because I want to get subtraction because I want to do 45 minus 30. So what this tells me is this formula, this function, is going to be equal to sine of my first value, which we call alpha, times cosine of my second value, which we call beta, minus cosine of my first value, beta, like some of you, betas.
What's that?
It's a very bad insult, don't repeat.
No, I'm repeating my math teacher. Cole, you're a beta. What does it mean? Does that mean like you're a...
Well, alphas are the ones that are the leaders of the pack, right?
Yeah.
Betas are the ones that are followers.
You're a follower. So they're little...
Now you know.
Now they're little...
Okay, so in this specific example, this one's going to be my alpha, this one's going to be my beta. And remember, those two are on the unit circle, which means when I plug in all these values, I can jump to the unit circle and find all of these answers without a calculator. I come over here. My formula becomes sine of my alpha value, that is 45, times cosine of my beta value, 30, minus cosine of my alpha value, so cosine of 45, times sine of my beta value, which is 30. All right, Cole,
What?
you're closest. Let's see how well you remember. Once you've gotten to here, unit circle is our bestest of bestest friends. So I have to first take these problems and discover which values actually get me to the one I want. I want 15, 45, and 30 will do it. From there, I then take these values, plug them into the specific formula for this. I'm doing a difference problem because it's 45 minus 30. And I plug in each one into the respective spots for alpha and beta. Cool? Your answer, please. As a reminder for everybody else who may be doing it at their desk, sine of 45 tells me you need to go to 45 degrees and read the y value. Go to your circle, 45 degrees.
2 over 2.
Y value?
Square root of 2 over 2.
Square root of 2 over 2. My first piece. Times cosine of 30 degrees. As a reminder, cosine is the x value. So I'm going to 30 degrees. I go to the x value. What is that x value? Square root what?
3 over 2.
Beautiful. Minus. So I did sine of 45. I did cosine of 30. Minus. What is cosine of 45?
Square root of 2 over 2.
Times. What is sine of 30?
1 over 2.
1 half. Now, this is the part where I have to get a little bit right. You now have to simplify this problem.
So do all like the beta and stuff?
Oh, I would. You better believe, like, I'm only showing that formula so that people who are just looking at the screen can know where that got from.
Oh, so why'd you put that?
Because I could. Next problem I won't. I'll jump straight to here. Because I'm like, I read off the page, find it on the page, find it. Your problem now. Alright? Okay, so I have to simplify this down and then I actually have the solution. Now, unlike with a calculator that will give you a decimal version, this will give you a fractional version, usually with some radicals flipped around in it, and that's fine. Leave it there. The goal of this is I get to a solution without a calculator. How nice that solution is up to us and the problem. So in this case, let's take about each of these pieces, and let's remind us of some rules from algebra. So far, we have applied the sum difference rule. This is a difference problem. I use the two values of 45 and 30 to get me to 15. I use that formula, I plug into that formula, getting these four solutions. But now comes algebra. Simplifying. I have two things being multiplied. I have to deal with this separately. Then subtract the other two being multiplied. Let's do it. First one. Square root of 2 over 2 times square root of 3 over 2. What does that multiply to?
Number. I just got here.
Nope. That's the problem with this section. These formulas are not hard in this section. But I'm telling you, you have to do fractional math again. That thing you wanted to block out from your elementary school days. And now I'm asking you to do it with trig functions and radicals. Woo! Yeah. What a day to be alive. Yeah, cool. Okay, so as a reminder, I multiply top times top,
Square root of
bottom times
6.
bottom. The top would be the square root of 6. Bottom times bottom would be 4. Minus top times top.
Square root of 2 over 4.
And now I combine.
Square root of 4 over 4.
Be careful. When I combine these two, because they're in radicals, I cannot directly subtract them. Addition and subtraction inside of radicals works. Addition and subtraction outside does not. This becomes the very interesting problem. Square root of 6 minus square root of 2 over 4. Now, if you grab your calculator out, depending on the calculator you have, if you type in sine of 15 degrees, which was the original problem, you will either get this answer or the decimal equivalent. Let's see, who's got one of the Casios with them?
No, I do, but I can't use it. Can't use it, no.
I want you to check your answer this one time.
Nope.
Pull it out, come on.
I can't.
Don't lie to me.
You said I can't.
You're right.
Not for this section.
You're right. But I'm going to give you vision for this one problem. One problem. Type in sine of 15. Make sure you're in degrees.
It's that exact chrome on it.
Oh, look at that. It's that exact thing. If I grab my calculator, which only gives me decimal versions, if I type in sine of 15 degrees, make sure it's in degrees, it is sine of 15.
Can you calm him down?
I get the decimal,
which is 0.26.
0.2588. Yeah.
Man, do you need some energy? Yeah, dude, I'm pumped up
Now, one more time. What this does, this broadens what I can do without needing a calculator. For a long time, this is what you had to do. You had no choice. If I wanted to do sine of 15 for a complex math problem, if I wanted to do it for, applications in physics, if I wanted to do it for applications of things like telemetry, I had to do it this way because I didn't have a calculator to do it for me. Modern day, of course, we have these tools available to us, but a lot of Trig is understanding how these pieces fit together. This is one of them. So,
Is there 5?
to the next problem.
2588.
Yes, 0.2588. These problems, you're strongly encouraged if you have one of the Casios to check your results. But whenever I grade your problems, I will be looking to see the work that you did. Because quite frankly, all of these can be done with a calculator at some point.
Nice restroom.
Yes, sir. So, section 1, calculator is completely useless. Can't do a single thing. Section 2, calculator can do all of it, but we're showing you how to do it without one. Alright, next problem.
So you're showing you don't have to. Yeah, that's what I think.
When you leave this class, you don't have to anymore.
Oh, bet.
But until then, let's do cosine of 105 degrees. Now, first thing I want to point out, 105 is not on the unit circle. So I cannot just jump around and use that fact. I have to find either an addition problem or a subtraction problem that will get me to 105. Now, examples. Terrible examples. 100 plus 5. Yeah, it adds to 105, but neither of those are in the unit circle, so don't suggest them. 104 plus 1. Neither of those are in the unit circle. Do not suggest them. Okay? Suggestions.
145.
Scott?
Oh, yeah, I see.
What'd you say, Scott?
150 minus 45.
That's a good one. So Scott said, let's do cosine of 150
What Scott said.
minus 45. That's pretty good.
Or you could do 60 plus 45.
I could do 60 plus 45. Again, there are a lot of ways I can do these problems. So,
Or 135 minus 30.
I could do, oh yeah, that's a good one. Like, and you can think of some more if you want.
I like the 60 plus 45.
And you'll find that whenever I do these problems, I try to stick as much as possible in the first quadrant. Again, eventually, by next week, I want that unit circle off the table again. I want you to do these out of unit circle.
There's no
Okay?
way.
No way. You did it once before, but do it again.
Ain't no way. Ain't no way. Okay.
So, if I want to do that, it makes a lot more sense to be like, let me make it as simple as possible. Put it in the first quadrant. The numbers are easiest to remember there. There's no negatives floating around. That's why I typically do it. Now, as we're getting used to it, I want to unit circle out because I want you to get used to the formulas. But again, next week, I will have those unit circles put away. Alright, Luis, there are 3 versions.
These aren't. No.
What do you want to do, man?
60 plus 45.
Oh, you're going to go with the crowd? Oh, I was hoping you'd be a rebel. But you know what?
Where are these
Let's
at
do it.
on our papers?
If you go to it, so my cheat sheet has some difference. Yours might have addition, subtraction.
Oh, yeah.
Wait a
I see
minute.
it.
So, like, if you're adding, you're basically subtracting. Like,
So if you look at the formulas, there are some unique dualities, but they don't always work. If you look at sine actually matches perfectly. The plus in the sign becomes the plus in the answer. The minus in the sign becomes the minus in the answer. But cosine is actually the opposite. And tangent, half does one, half does the other. And so these formulas are why I print these cheat sheets out. Makes we have fewer mistakes. Let's go to our problem on the board. If we're going to do 60 plus 45, as suggested by Scott and verified by Luis, let's do it. Cosine of 105. How do I do it? I'm going to do cosine of 60 plus 45. So the sum formula for cosine says we do cosine of my alpha, which I'm going to leave blank, times cosine of my beta, minus sine of my alpha, sine of my beta. Let's plug in those numbers. Cosine of my alpha is 60. My beta is 45. My alpha is 60. My beta is 45. You might also ask the question, well, we did 60 plus 45. What if I did 45 plus 60? So, close it. Okay. Levi, you got those numbers in front of you, right?
Square root of 2 minus square root of 6 over 4. What number?
Unit circle?
I got you.
Let's find the answer.
1/2.
1/2 for cosine of 60?
Yeah.
Times cosine of 45?
Square root of 2 over 2.
Here, 2 over 2.
Times, that is no.
Yeah. Minus sine of 60?
Square root of 3 over 2. Times square root of 2 over 2.
Okay. Looks good so far. Before we go any farther, there are pieces. And then simplify. Simplify the first piece. 1/2 times square root of 2 over 2. Top times top is square root of 2. Bottom times bottom is 4. Minus square root of 3 times square root of 2 is square root of 6. Top times top. On bottom, 2 times 2, 4. I simplify what I can. They have the same denominator. That's good. So square root of 2 over 4 minus square root of 6 over 4 becomes square root of 2 minus square root of 6 all over 4. Now, this is the calculator answer. But below my Casio, that's what we'll say. If I pull out my TI or my usual cell phone calculators, cosine of 105 will give me a decimal, which in this case should be a negative decimal. It actually makes a lot of sense. In the second quadrant, cosine is negative in that quadrant. So that's how we do it. These are the sum difference rules, or on your pages, the addition subtraction rules.
This is so much easier than what we just did.
Oh, I bet there's a way I can make this harder.
No, I mean, yeah, I bet there is, but
Okay, so
I should get.
we chose 60 plus 45. We have 4 minutes remaining. I don't want to do another problem. I'm going to ask us to do this problem differently.
What?
Alright, so we're doing 105. I would like you to do this with the following 2. You already know the answer.
So which
That's
one,
nice.
Which one do you want us to do?
I want you to do.
Shut up, bro. Come on, man. We got 4 minutes. Hurry up.
Oh, how about 135 and adding negative 30?
Nope, I'm done.
Ooh. Ooh.
Once you saw the
Can I
negative
change
answer.
that to just 135 minus 30?
No.
Why? It's basically the same thing.
Ah, but I have to use different rules if I do a plus sign versus a minus sign.
Yeah, I'm done. That's a good lesson.
So, as a reminder, this is why I wanted to bring it up. I have all the negative versions as well, which, as a reminder, on the unit circle are not listed, but they're there. As a reminder, positive 30 is up here, negative 30 is its flipped version on the other side. So 330 and negative 30 are the same thing. Positive 45,
Negative 45.
negative 45 is at positive 315. 60, positive 300 becomes negative 60. When we come in tomorrow, we will be doing something that involves some negatives. Don't let those freak you out. You will need to have those skills down too.
But it's.
And again, tomorrow, no calculators allowed. We're doing every one of these by hand. I know, I ask an awful lot.
Hey,
What
can
can
I
I
get
say?
one?
Alright, we'll pull up the video. And next block, I'll record any other problems people ask for. I'll have to do 35.
Thank you.
We're going to spend the time up until lunch and plus a few minutes after lunch. Use as many questions as we can. But when the time runs out, move on. 35. We have the following. Secant squared of negative x minus tangent squared of x over tangent of x times 2 plus tangent of x over 2 plus cotangent of x. Oh, that's 36. Oh my god. Thank you. I was going to keep going. I was like, all right. All right, 35. Let's try that one more time. Cosecant squared of x times 1 plus sine squared of x. And we want to show, or I should say prove or disprove, x equals cotangent squared of x. So this is a maybe. Alright, so what I'm going to do, again, I follow the same basic protocols. I pick the hardest side that it looks like. I'm going to try to modify that side, and hopefully I get cotangent squared. If I get anything that cannot be modified to cotangent squared, it's wrong. If I get cotangent squared plus 1, it's wrong. It's not cotangent squared by itself. So, let's start with the hardest side. Cosecant squared times 1 plus sine squared. Okay. Algebraically, I have a lot of steps I can do. Trigonometrically, I have a lot of steps I can do. So take a look at the board. What's something I can try? I could do transfer cosecant into 1 over sine. I could distribute. What else? Yeah, that's what Dan did. I could try to use a Pythagorean identity, but those usually have 1 minus sine squared. So if I saw 1 minus sine squared, I'd probably be immediately jumping on board with that one. But with 1 plus sine squared, I could do it. It's going to take more work though, so I'll hold off on that one. Let's try these two. Okay, I like them. We'll go with them. So we're going to use 1 over sine for the cosecant, and I'm going to distribute it. I'm going to do that all in one step. So this becomes 1 over sine squared And then I'm going to take that and distribute it to both terms. So this becomes, and I'm going to write out my full step, 1 over sine squared times 1 plus 1 over sine squared times sine squared. So I distributed the 1 over sine squared to each term, times the 1 and times the sine squared. What happens now? Yeah, what changes?
Thank you very much.
No problem, man. Everything changes. Come on, be specific, man.
The one changes cosecant,
So this one changes back to cosecant.
and the sign would change to 1.
A 1. Sine squared and sine squared cancel because 1 is on top of a fraction, remember? On top of a fraction, and the other is on the bottom. They cancel out, leaving just a 1. Add cosecant squared of x plus 1. Well, I've seen cosecant squared before. Maybe I try an identity. Do we have a identity that deals with cosecant squared plus 1? If not cosecant squared of 1, do I have one that deals with just cosecant squared? Yes. What is the one that involves cosecant squared? Cosecant squared is equal to?
Square.
Anything else?
One.
Plus 1. So, everywhere there's a cosecant squared, I'm going to do a substitution and replace it with cotangent squared of x plus 1. So this becomes cotangent squared of x plus 1 from the cosecant squared, and then plus 1 from the rest of the problem. When I simplify, there's nothing to do to that first of the parentheses. I put it there to remind myself that plus 1 was already in the problem. So this becomes cotangent squared of x plus 1 plus another 1. Those two, of course, just become cotangent squared of x plus 2. And at this point, I look at it and go, no, this never works. It is not equal cotangent. It equals cotangent plus 2. So the answer to this question is disprove. The answer to this question is false. The answer to this question is no. Take a pick. I prefer false. Because when it comes to proof, there's either two types of statements. It's either true statements or false statements. If it's not true, it's gotta be false. Yes, but the problem said, unless somebody told me the problem wrong, the problem said just cotangent squared of x. Was it wrong? Yes. Yeah. So since what we got does not equal the right-hand side, that makes this false. 39? 37. 37. Can I erase the screen? Am I good to go? Or do I need to keep it up there for a few seconds longer? Okay. It will also be included in the video. Okay, 37. No. Yes, 37?
37, yes.
I already did 36, so tangent of x over secant of x times sine of negative x equals cosine squared of x. I want to prove or disprove. Is this true or false? Suggestions.
I think the negative of the sign.
So you're asking me to use the left-hand side first?
Sure.
There we go. Tangent of x over secant of x times sine of negative x. You said that the negative out first?
Yeah.
This will become tangent of x over secant of x times negative sine of x. Now, I'm going to make a small change right now before I do anything else. I'm going to move that negative to the front. That way I do not confuse this with minus sine of x. So, My next step is going to be negative tangent of x over secant of x times sine of x. I'm doing this because I know who I am as a person. I am the person who will forget that with a negative sign and mess with this problem. Learn who you are. For reals. Alright? Next. So far, everything you've done is perfect, by the way. Next. You are correct. How do you know that? So he uses the quotient rule and the reciprocal rules. This is negative. On top, he'd have sine over cosine. On bottom, he'd have 1 over cosine times sine of x. So we change everything into sines and cosines, which, remember, is step 4. And from there, we then use the KFC method, or multiplying by the reciprocal. We write this as negative. The top stays the same, so sine over cosine. The bottom flips, so instead of 1 over cosine, it is cosine over 1. And don't forget, there was still a sign in the problem. And then, as Brian was saying, the cosines will end up canceling, leaving us with negative sine times negative sine, negative sine times just regular sine, which would be negative sine squared. This one is also false. By using the I can see that this is equal to cosine of x minus 1, which is wrong. Enjoy your lunch. We'll continue when we get back.
39 when we get back.
39? Sure.
Can I use this? Can we use this?
Heck no.
You said that to send it to her.
9. Let's go to 39. I hope it is obvious from here that those two are not the same. Negative sign is not the same as cosine. Okay, 39. So this one, depending on how you approach it, there are a couple different ways to do so. So this will be kind of fun. 1 plus sine of x over cosine of x. Does this equal cosine of x over 1 plus sine of x? Alright. Suggestions.
Get rid of the negative sine of x.
Oh, wait.
On the second one.
Oh, on the second one, thank you. So you're suggesting we work with this side, right? Yeah. Okay, well, let's do that. So we have cosine of x over 1 plus sine of negative x. Okay, it says, let's take a negative sign and move it out. So we get cosine of x over 1 minus sine of x. Okay, that's looking promising. Next.
1 minus sine of x is cosine squared.
Not true. That's 1 plus sine, or 1 minus sine squared. If there was a square there, that would work. But maybe there is a way to get a square there. So this is one we talked about in class. In algebra, there is always the idea that I can multiply an equation by 1. Now, usually we don't multiply by 1, multiply by something that is the same as 1. 1 plus sine over 1 plus sine is 1. Remember, the top and the bottom are the same, so they cancel, leaving 1 behind. Why would I do this in particular? Well, because this particular equation is called a conjugate, and something unique happens when I use it. So this is from algebra 2. I am multiplying by a conjugate. Here we go. On the top, I'm going to leave it as cosine of x times 1 plus sine of x. The reason why will become apparent here in a little bit. On the bottom, I'm going to FOIL this problem. 1 minus sine of x times 1 plus sine of x. Now, the reason I multiply by a conjugate is because this creates a situation referred to in algebra called difference of squares. When I FOIL this out, the bottom has something unique that happens. Here we go. FOIL. So the top, I'm keeping the same. Now the other reason I know this is a good step is because look what I've added to the top now. I've added the 1 plus sine of x, which I want in the problem. So this is another reason that tells me, hey, look to your solution to tell you kind of what you want to do. If I want 1 plus sine of x to appear, it could appear naturally, or I could force it to appear by multiplying by it. But I have to do it to the top and the bottom. So the top stays the same. The bottom I'm going to FOIL. So 1 times 1 gives me 1. 1 times positive sine of x gives me plus sine of x. Negative sine of x times 1 gives me negative sine of x. And negative sine of x times positive sine of x gives me negative sine of x squared. Why is that so good? Because in the bottom, a conjugate has this unique property where the middle terms of FOIL end up canceling. So the positive sign and the negative sign go away, leaving something that Kylie was referring to. We end up with cosine of x on top times 1 plus sine of x all over 1 minus sine squared of x. That is one of our Pythagorean identities. So Kylie saw that we wanted to use the Pythagorean identity, but we couldn't because of how it was currently written. So I modified it using the piece that my solution wanted. Now, when I modify it, Kylie, what happens at the bottom of this thing?
It goes to cosine.
So we end up with cosine of x on top times 1 plus sine of x. And on bottom, the bottom becomes just cosine squared of x. Jolie's making the motion. What are we going to do, Jolie?
Cancel.
Yep, we cancel. One of the cosines on top with one of the cosines on bottom. And what's left behind? 1 plus sine of x over cosine of x. I'm so glad you picked the right-hand side. Working from the left-hand side is a disaster waiting to happen. Oh, it's bad. Just trust me. It's bad. This is one of those where like one side is not easy, but it's doable. The other side is like, oh, I want to bash my brains against the wall. Thank you very much. I was through that. You are finished. Please place them up here in front. They are due tonight, so you may turn them in the Google Classroom as well. If you are unable to turn them in tonight for a reason, they'll also do them tomorrow, of course. Table in front. And with the remaining of the time that we have today,